So we still have to discuss the resolving power of the diffraction grating for topic 9.4 to end. So first of all, what's a diffraction grating? From the previous topic, which is 9.3, you will be introduced to diffraction grating, but let me say it quickly here. So a diffraction grating is a piece of glass, okay? Usually this piece of glass, it doesn't allow light to pass unless light is passing through its slits. So basically it's a piece of glass which made up of many slits, a lot of slits, okay? And usually, so light is going to pass only through these slits. Usually they don't give you the separation between the two slits, but what they give you is the number of slits per millimeter. So in this case, to find the distance between the separation or the distance between the successive slits, all what you have to do is to divide 1 over x, where this x is the number of lines or the number of slits, okay, of lines per millimeter, okay, and the unit of x, it's millimeter minus 1. So this is the distance between two successive slits. So between two slits or two consecutive slits. Now, if light is coming toward a diffraction grating, so let's say that this is a diffraction grating, okay, and this is the light getting into this diffraction grating. So what will happen is that on a screen far away, so this is a screen, you will notice that this is the midline here. So you will notice that the intensity pattern will look like spikes, okay? So it will look like lines. So this is the central max, this is the first maximum, this is the second order maximum, and here the same thing from the other side, the first max, the second max, and so on. So if I'm drawing the intensity versus the angle, usually the angle is in radian, this is how the intensity pattern is going to look like. So they are sharp, they are thin, and they are of equal intensity. And we have learned also from topic 9.3 that in order to find the angular separation, this angular separation between the central max and any maximum, like here the first max or the second max and so on, so this is the first order, second order, and so on, then I have to use this equation, which is d sine theta equal to m lambda, where m take the values of 0 for the central maximum, 1 for the first order, 2 for the second order, and so on. As I told you, this d is the distance between two successive slits. This is the angular separation between the central max and the first max or the second max, or according to the order that I'm talking about, and this is the wavelength of light. Now, if I'm emitting white light on this diffraction grating, then in this case, at the middle here, you will see a white light, okay? But for the first order, you will not see a white light. You will see the colors, and the farthest color will be the red. The farthest color will be the red, and the nearest one, let me draw a red here, and the nearest one is going to be the violet. And of course, the colors are going to be in between. So the closest one is going to be the violet, and so on. So here you will find the blue, for example, and so on. The blue, the green, and so on. So basically, if I would like to find what is the angular separation between two colors, so if there is like two wavelengths that are very close to one another in value, then the spikes are going to be very close to one another. So maybe there's a red and there's a red which is of a slightly different wavelength. So in this case, the ability for the diffraction grating to resolve these two spikes, we can find it using the resolving power equation. So this resolving power equation, it's equal to the average wavelength of the two colors over the smallest separation, or basically it's the difference in the wavelength. So this lambda, it's the average wavelength. How do we find it? So for example, if he is talking about two colors, so all what you have to do to find lambda is simply you add the wavelength of the two colors that he's talking about and you divide it by 2, and this is the difference in wavelength. So simply it's lambda 2 minus lambda 1, or lambda 1 minus lambda 2. It depends on which one is the greater one. So this is the resolving power of a grating. And it's equal to, this resolving power, it's equal to lambda over delta lambda, but it's also equal to the order. So this order is the order which is being observed. So if I'm looking at the first order which is being observed, I'll take it as 1. If I'm looking at the second order of the colors, I look at 2, and so on, times n, where n is the number of slit which is being eliminated. So here, if light is going on only 3 slits, let's say, okay, then n will take the number of 3, and so on. Sometimes, so first this is the order being observed. And this n is the number of slits eliminated. Okay? Sometimes they don't give you n, which is the number of slits being eliminated. Sometimes he gives you the width that being eliminated. So in this case, to find n, all what you have to do is to use this relationship. So the width of light is equal to, the width of light falling on the grating is equal to the, it's equal to the number of slits over d. Actually, it's equal to the number of slits, which number of slits times the width of one slit. So this is the width of the light falling on the grating. Okay, so this is the number of slits times the size or the separation between the two slits. This is how I might be using this equation to find n, where of course d is 1 over x. So basically, this is the equation that we use in order to find the resolving power of a diffraction grating, and that's it. So now we need to do some practice in order to know how to use this equation. Okay, one more thing that I would like to say, the more the angle of separation between the spikes, the more the resolving power as well. Okay, so let's solve some examples on this equation so that we understand the concept more. So here he's saying that a diffraction grating is used to observe light of wavelength 400 nanometer. So this is the average wavelength. The light eliminate 100 slits of the grating. So this is the n. Okay, and this is the average wavelength. What is the minimum wavelength difference that can be resolved? So he's talking about the minimum wavelength difference, and he's asking for delta lambda. So delta lambda, it's the minimum difference in wavelength that can be resolved in this case. When the second order, so here he has given you m equal to, so when the second order of the diffraction is viewed. So which equation I'm going to use? This only equation which we have. So we have the relationship which is, so the equation is R equal to the ratio which is lambda average over delta lambda. It's equal to the order times n. So he's asking for the minimum difference. So he's asking for delta lambda. So delta lambda in this case, it's equal to the average wavelength. Sometimes he give you one wavelength and this is the average, and sometimes he give you both of them and then you have to find the average. We will see this in another example. Over the, so over m n. And I just substitute, so the delta, the difference in The wavelength that will be resolved, in this case, it's 400 nanometers times 10 to the power of minus 9 over the second order times the number of slits. So that's it. All what we have to do is to just do this, and we will be able to find the answer. So in this case, the answer for this one is going to be equal to 2 times 10 to the power of minus 9, or in another word, it's 2 nanometers. Here he's saying that there's a light is incident on a diffraction grating. The wavelength of the two spectral lines of light differ by, so this is the difference in the wavelength, and have a mean wavelength, so this is the average wavelength. The spectral lines are just resolved. They are just resolved in the fourth order of the grating. What is the minimum number of, so here m is equal to 4, and he's saying what is the minimum number of grating lines that were eliminated. So I need to find n. So in this case, m times n, it's equal to the average wavelength over the difference. So n in this case, it's equal to the 590 nanometers over the 0.59 divided by 4. So here I have to multiply this by 4. I'm not going to convert from nanometers to meters because it's going to be cancelled out in either cases. So in this case, I can write it as such. So as if I remove the decimal place, like 1, 2, 3 decimal places, so it's times 10 to the power of minus 3 times 4, and the answer is going to be 0.25 times 10 to the power of 3, and then you can move the decimal place 3 decimal places, which end up as 250. Light is incident on a diffraction grating. The wavelength line, so this is a bit different. Here he has given you the two values of the wavelength, so you have to find the average and you have to find the difference. And he said that they are just resolved, so we can use this equation, but for the second order spectrum, how many slits of the diffraction grating are eliminated? So first, the lambda average, it's the addition of these over 2. 600 plus 601.5 times 10 to the power of minus 9. No need here to convert because it's a ratio of wavelength over 2. Okay, and the difference in wavelength, as you can see, it's 1.5. Okay, and m is 2, the second order. So this is m. So to find n in this case, it's the average, which is this, over 2. So approximately it's 600. Divided by 1.5, so divided by 3 over 2, okay? And multiplied by 2. Okay, so basically this is going to be equal to 3 here, and this one is going to be equal to 600 plus 601.5 over 6, which means that approximately it's 200. Okay, because if you add these two together, or if you divide each part by 6, 100 plus 100 approximately will give you a 200. Here he's saying light passes through a diffraction grating, which quantity must be decreased to improve the resolution of the diffraction grating. So if you look here, he's saying that the diffraction grating spacing, if we decrease the space between the diffraction grating, here I'm talking about D. So if D is decreased, then N is going to be increased. Do you remember this? Do you remember this relationship? We said that the width is equal to N times D, which means that D is the width over, or basically N is the width over D. So if D is decreased, it means that the more the number of slits that, so light will hit more number of slits, which will increase the resolution, okay? So this means that, yes, this is the answer. If you would like to continue through the givens, he's saying the number of grating lines eliminated by light. No, this one basically, if I decrease n, this will decrease the resolution. So as if this is opposite to this one. The number of grating lines per millimeter. So I'm decreasing this, which will increase d because d is 1 over x. The spectral order being observed. So if I increase m, basically the resolution is going to increase. So basically it's only A. Now let's solve some paper 2 questions. It's only one question. He's saying it's part of a whole paper 2 question, but I'm taking only the part which is related to my idea. So he's saying the double slit is replaced by a diffraction grating that has 600 line per millimeter. So this is X. The resulting pattern on the screen is shown as such. So this is the intensity versus the angle. And there was 9D, he asked me to distinguish between the double slit and the diffraction pattern. So I'm going to answer this in another video, but I'm going to answer 9E. He's saying the yellow light is made from two very similar wavelengths that produces two lines in the spectrum of sodium. The wavelengths are this and this. Okay, so now I can find lambda average, and I can find the difference of these lambdas. These two lines can just be resolved. So I need to see this difference, which is resolved in the second order for m equal 2 of this diffraction grating. Determine the width of the beam width of light incident on the diffraction grating. So in this case, I need to find n, then multiply it by d, which is the distance between two slits, to find w. So first, let's get lambda average. Lambda average here is 588.995 plus this over 2. If you do it, you have to get the answer of 589.2935. So this is the lambda average. The difference that I need to resolve, simply it's 589.592 minus 88.995. And the answer is going to be, in this case, 0.597. So I need to find first n. To find n, it's lambda average over delta lambda times the order, which is, in this case, if you put the order as 2, you will get that n is 493 slits being eliminated. Now, to find the width of this beam, all what you have to do is to multiply n times d, but I don't have d, but I have x, and d is 1 over x. So it's equal to 493 over 600. So the width of the beam will be 0.82 millimeters. I kept d in millimeters, so that's why the answer is in millimeters. You can convert it if you want. So that's it. This is the resolving power of the diffraction grating. So that's it.